Imagine a time before time, a space before space, a moment of infinite density and temperature, a singularity. This is the beginning of our universe, the Big Bang. And today we'll embark on a cosmic journey exploring the birth, expansion, and future of our universe. A blinding white light. Then, in the blink of an eye, a cosmic explosion, the Big Bang, unleashed a flood of energy and matter. As it cooled, a primordial soup of particles formed. Protons and neutrons emerged, the building blocks of atomic nuclei. The universe was awash in a sea of photons, the particles of light. Nuclear fusion formed the first atomic nuclei, primarily hydrogen and helium. Gases were opaque due to such high temperatures. The cosmos entered a period known as the Dark Age, yet within the darkness, the seeds of stars and galaxies were sown. Dark matter, an invisible substance, provided the outline for these celestial structures. Massive, short-lived stars called population 3 stars emerged, emitting ionizing radiation. This radiation stripped electrons from atoms, re-ionizing the universe. Galaxies began to cluster together, forming a cosmic web. Gas clouds collapsed under gravity, forming new stars and planetary systems. Earth, a unique oasis in the cosmos, provided the right conditions for life to emerge. The exact origins of life remain a mystery, but is believed to have started in the Earth's early oceans. How did the universe begin? What forces shaped its destiny? The Big Bang Theory. Supported by compelling evidence such as redshift of distant galaxies, the cosmic microwave radiation, and the abundance of elements, offers us a glimpse into the universe's birth and evolution. Electromagnetic radiation is a form of energy that travels through space in waves. It encompasses a wide spectrum, from low-energy radio waves to high-energy gamma rays. With visible light, violet waves are the highest energy. Red waves are the lowest energy. So now imagine a train approaching you, blowing its whistle. As it gets closer, the pitch of the whistle seems to increase, and as it moves away, the pitch decreases. This is known as the Doppler effect. Like sound, when a light source moves away from us, the wavelength of light stretches, shifting towards the red end of the spectrum. This phenomenon is called redshift. Conversely, if a light source is moving towards us, the wavelength shortens, shifting towards the blue end of the spectrum, known as a blue shift. Alexander Friedmann was a visionary scientist who in the early 20th century applied Einstein's theory of general relativity to the universe as a whole. He is known for making two famous assumptions, a cornerstone in modern cosmology, known as the cosmological principle. The cosmological principle suggests that the universe is both uniform and symmetric. Imagine a staircase that spirals infinitely upward. Each step represents a different point in space and time. If you were to look up or down the stairs, the overall structure would always appear to be the same. While an infinite staircase is a simplified analogy, it helps illustrate the core concepts of the cosmological principle. Just as the staircase is uniform and symmetric in all directions, the universe, according to the cosmological principle, is also uniform and symmetric on a larger scale. The only difference is it's dynamic, expanding, and evolving. If you were in a forest that was infinitely large, no matter where you'd look, you'd see a tree, right? In the 17th century, German astronomer Heinrich Wilhelm Olbers posed an interesting question. If the universe is infinite, and completely filled with stars. Then why is the sky dark at night? This is a question that has puzzled astronomers for centuries. It's known as Olber's paradox. Scientists have figured out that the universe isn't as simple as it seems. Here's why the night sky is dark. The universe has a finite age, and it began about 13.8 billion years ago with the Big Bang. Light takes time to travel, so we can only see a limited distance into the universe. And as the universe expands, the light from galaxies is stretched, making it fainter and redder. Our galaxies are much like the chocolate chips on a giant cosmic cookie. As the cookie rises, the chocolate chips on it move further and further apart. Hubble, an astronomer, peered into the night sky with incredibly powerful telescopes. He noticed something incredible. Galaxies weren't randomly scattered, but were moving away from us. And further they went, the faster they were residing. This is known as Hubble's law. And by measuring the redshift of galaxies, astronomers can calculate their distances and velocities. This allows us to estimate the age of the universe and gain insights into its future. As the universe expanded and cooled, it reached a point where photons could move freely throughout space. This event was known as recombination and occurred about 380,000 years after the Big Bang. The photons released during recombination have been traveling through space ever since, and today they form the cosmic microwave background. Have you ever wondered why we have such a rich variety of elements in the universe? From the hydrogen that fills our balloons to the iron in our blood, the answer lies in the incredible power of stars. The process of creating heavier elements is a bit complex. Stars, the cosmic furnaces, play a crucial role. Inside stars, intense pressure and temperature cause nuclear fusion to occur. The elements forged in stars are not lost, but are recycled throughout the universe. The universe, vast and mysterious, has captivated humanity. A closed universe is one that'll eventually stop expanding and begin to contract. Its geometry is spherical, much like the surface of a ball. An open universe is one that will expand forever. In this model, the universe's geometry is much like the surface of a saddle. A flat universe is one that is balanced and on the brink of expansion and contraction. Its geometry is like a flat sheet of paper. So imagine a cosmic tug-of-war between two opposing forces: gravity, which pulls matter together, and expansion of space, which pushes matter apart. Critical density is the dividing line between these two forces. So, what is the fate of our universe? Scientists have inferred three possibilities: the Big Crunch, the Big Rip, and the Big Freeze. A closed universe is finite and bounded cosmos shaped like a sphere. In this model, density of matter and energy is high enough to overcome the force of expansion. Eventually, the universe will begin to contract, drawing all matter and energy back to a single point, potentially leading to a big crunch. This catastrophic event could trigger another Big Bang, leading to a cyclical universe. If the universe is flat, its ultimate fate may be a slow, cold death known as the Big Freeze. Time itself may lose all meaning as there is no change or activity. The universe will exist in a state of perpetual stillness, a cosmic graveyard. An open universe is a delicate balance between expansion and contraction. This scenario is tied to the mysterious dark force of dark energy, which is accelerating the expansion of the universe. If dark energy continues to strengthen, it could eventually overcome the gravitational forces that hold galaxies, planets, and stars together. As dark energy intensifies, it would stretch the fabric of space-time, tearing everything apart in its path, like a snapped rubber band. If we add up all the masses of the stars, the total is less than 1/100th the amount to halt the expansion of the universe. However, there is something mysterious lurking in our universe. Imagine a cosmic stage where galaxies whirl and dance, held together by an unseen force. This mysterious force is known as dark matter and comprises 85% of the universe's matter. Yet it remains elusive, interacting with ordinary matter only through gravity. Dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Its presence is inferred from its gravitational effects on visible matter. Dark matter belongs in a category of matter known as non-baryonic matter. Unlike ordinary matter, which is comprised of protons and neutrons, non-baryonic matter is made up of exotic particles that we fully don't understand. The search for dark matter is one of the most exciting frontiers in modern physics. By unraveling the secrets of this elusive substance, we may unlock the fundamental nature of the universe and gain insights into its ultimate fate. By carefully measuring the distribution of dark matter, scientists can piece together the puzzle of the universe's shape and its ultimate fate. By studying how dark matter influences the large-scale structures of the universe, scientists have concluded that our universe is remarkably flat. Ever dreamed of visiting ancient civilizations or peering into the distant future? Time travel, once confined to the realms of science fiction, has captivated imaginations for centuries. But is it merely the stuff of dreams? Or could it be a reality lurking just beyond the horizon of scientific understanding? While planets and stars are subject to the laws of classical physics, the quantum realm operates by different rules, and some scientists speculate that by manipulating quantum particles, we could offer a unique approach to time travel. Subatomic particles have already been known to move faster than the speed of light, travel back in time, and even get caught in a closed loop. Quantum entanglement, a phenomenon where particles become interconnected regardless of distance, could potentially be harnessed to create time machines. By manipulating the quantum state of particles, it might be possible to influence the flow of time itself. But let's pause for a moment and consider the ethical implications of time travel. One of the most famous paradoxes is the grandfather paradox. Imagine traveling back in time and killing your grandfather before your father was born. This would prevent your own birth and causing a logical contradiction. So could time travel be inherently impossible, or are there mechanisms in place to prevent such paradoxes from occurring? As we've journeyed through the cosmos from the Big Bang to the mysteries of dark matter and time travel, we've glimpsed the extraordinary beauty and complexity of the universe, from the vast expanse of galaxies to the world of quantum particles. There's a lot more to discover.